Hello everyone, this is the brief review of Chapter 4, Part 1. I decided to break up Chapter 4 into two short videos because there was kind of a natural breaking point, and it's really important that you understand the first part of the chapter before we move on to the second part. So I thought I'd give the first part first and then give you a chance to review that, really get it solid before you move on to part 2. This will cover sampling error, the first part, and then in the second part we'll cover confidence intervals. One of the reasons why you're taking this course is to learn how to use statistics. And the only reason why statistics are required is because of a problem known as sampling error. So I'm going to use this example to illustrate the problem of sampling error. You have a population of college students, and we're interested in finding something about them. In this example, we want to know if there's a difference between their satisfaction scores taking a face-to-face class versus an online class. Of course, I can't study the entire population, so I have to take a sample. And then I randomly assign part of the sample to take a face-to-face class and the other part of the sample to take an online class. After they experience the classes, they take a questionnaire, dependent variable, and I get their mean satisfaction score for the face-to-face class. I get the other sections, mean satisfaction score for the online class, and then I get their mean difference. This mean difference is called a statistic. And I use this statistic to estimate the population parameter. In other words, what the population would be like if half of it took a face-to-face and half of it took an online class. What would be the difference in the satisfaction in the population between those two subsets? Again, if I did the study on the entire population. When I do that, I'm inferring that the results that I get from the sample would be pretty close to the results I would get from the population. And when I do that, it's called inferential statistics. The problem is that samples rarely represent the population perfectly. In other words, the answers that I get, or the statistics that I get from the samples, are rarely going to match perfectly the population parameters. And when there is a difference between a sample statistic and a population parameter, that is called sampling error. Now, the amount of sampling error a given study has is influenced by two things: sample size and the existing variability in the dependent variable. If you want to decrease sampling error, you can increase the sample size, or you can decrease the variability in the dependent variable, perhaps by increasing the precision with which you measure that dependent variable. There are equations that you can use to estimate the sampling error that any given study is going to have, actually before you do the study. That's really important and valuable to do, because if you want to, sometimes it takes a lot of money and expense to conduct a study. And it would be really bad if you completed a study and then realized at the end, after you put all the money and effort into it, that the study isn't going to be powerful enough. It isn't going to have enough sensitivity to detect what you're trying to detect. That's a fancy way of saying it would have too much sampling error. So what you can do is you can compute expected sampling error before you do the study. You plan your study, you decide how much sample size you need based on these formulas. You have two formulas here. They're very similar. This is the formula you would use if you know the population standard deviation, called sigma. If you don't know the population standard deviation, you would use this formula. You would just use the sample standard deviation, and that would be your best guess at the sampling error you'd expect in your study. Now, if you really want to understand how sampling error works, and how it has its impact on studies, you really need to understand something known as the distribution of sample means. The definition of a distribution of sample means is that it contains all of the samples of a given size that are possible that you could get when you are sampling from a population. In other words, it's all of the possible samples you could get when you're doing a certain study. Whenever you are taking a sample, you are conceptually sampling from this distribution of sample means. And that means if you understand the characteristics of the distribution of sample means, it will allow you to compute your expected sampling error. It's because of the characteristics of the distribution of sample means that we can compute expected sampling error with those two equations I showed you on the previous page. So what's going to come next is an explanation for why those formulas work. And that may not sound that interesting, but it's really fundamental to if you're going to understand concepts that are to come later in this chapter and all of the subsequent chapters. I cannot stress enough that the rest of this semester is going to be based on your understanding of how sampling error works. So I'm going to walk you through what a distribution of sample means is and how you would compute it. And it's going to be, you'll see that it would be very difficult to actually create a distribution of sample means. But luckily, at the end of this video, you're going to see that we don't actually have to build it because of something known as the Central Limit Theorem. The Central Limit Theorem allows us to predict the important characteristics of the distribution of sample means without having to go through all of the trouble that it would take to build it. But I do want to show you all of the trouble we would have to go through to build a distribution of sample means so that you can understand it and also really appreciate the importance of the Central Limit Theorem. So let's suppose that we have a population distribution over here that is normally shaped, and it has the parameters of a mean of 50 and a standard deviation of 10. I'm planning on doing a study, and my study is going to have a sample size of 25 people. So I'm going to randomly select 25 people from this population. And then I'm going to plot their mean. Then I'm going to do it again. So I'm going to take the 25 people that were in the previous example, and I'm going to, or the previous sample, I'm going to throw them back into the distribution. Then I'm going to randomly select 25 people. So it's possible that I could get the same people in the second study, or at least some of them. So I'm going to do that again, and then I'm going to plot that mean. And then I'm going to keep doing this over and over and over and over again until I get every single possible combination of 25 people from the population. Now let's think about what that means. If Bobby's in the population, I'm going to get Bobby paired with every other possible combination of 24 people and compute their mean every single time. Compute that mean every single time. Then I'm going to have to do that for Harriet and Leon and so on. So for every single possible combination of 25 people, I'm going to plot their mean. And if I do that, I'm going to get a distribution of sample means. Now that would be a ton of different samples. If the population is large, that would be impossible to do because there's so many combinations that there's no way I could possibly do them all. But if I did, this is what I would come up with, a distribution of sample means that looks like this. Now I want you to notice important characteristics about the distribution of sample means. First, look at its shape. It's normal. It has a normal shape, just like the population had a normal shape. The second thing to notice is the population was centered on 50, and then it spread out from 50, but the peak is under 50. The most common, or the mean of the population was 50. The most common score was 50. Now, if you look at the distribution of sample means, the same is true. The mean of the distribution of sample means is also 50. Now let's look at how spread out they are. The standard deviation in the population was 10. So that means in z-score units, we're going up z-score steps of 1, but in raw score units, we're going up and down in raw score units of 10, because that's the standard deviation. So you can see that we're fairly spread out. Look at what's going on over here. It's much less spread out. And that should make sense, because individual scores are going to be more variable than means, than sample means. Now, the relationship between the spread of the population and the spread of the distribution of sample means is not arbitrary. In fact, it follows that equation that I told you about at the beginning or earlier in the slides. It was the standard deviation of the population divided by the square root of n. So the square root of 25 is 5, so 5 divided by 10 gives us 2, and look, that's what these steps are, up and down. That difference there is called the standard error of the mean. That is sampling error. Now, if you remember back to the 95 rule, the rule for the distribution of a normal curve, 68.26% of all sample means will be between a z of 1 and a z of -1, or stated in raw score units, between a raw score mean of 52 and 48. So stated slightly differently, 68% of all possible sample means will be between 48 and 52. So in other words, 68% will be fairly close to the population mean. Most samples will represent the population pretty well. Most will be close to the population mean. And that's really important, because that tells us that sampling is a pretty good approach. Most of the time, a sample is going to be pretty close to the population mean. Most of the time, it's going to have at least reasonably small amounts of sampling error. And again, as I said, if that's too much sampling error, if we want to be closer than 52, closer than in this range, of course we could get something out here due to dumb luck or bad sampling. But if we want to get something even closer, we can just increase the sample size and then recalculate and see how close we get to what we were shooting for in terms of sampling error. So what we learned is that the distribution of sample means has specific characteristics, and the central limit theorem tells us what those characteristics are. The mean of every distribution of sample means will be equal to the population mean. The standard deviation, or the spread of the distribution of sample means, will be equal to the standard error of the mean, or sigma divided by the square root of n. That is a measurement of sampling error. And the shape of the distribution of sample means will have a normal shape if either of two characteristics takes place. First, if the original population had a normal shape, the distribution of sample means will always have a normal shape. Also, even if the original population had a very skewed shape, the distribution of sample means will have a normal shape if the sample size that you used to build that distribution of sample means is fairly large. Usually around 30 is enough to correct the skew of the population in the distribution of sample means. Now, if it's very skewed, the population is very, very skewed, then you might need a bigger sample. But generally, around 30 will yield you a normal distribution of sample means, even if the original population is somewhat skewed. So to review briefly, the central limit theorem tells us we don't have to go through all the trouble of taking every possible sample, plotting its mean, and doing it over and over and over and over and over again. We don't have to go all through that trouble because the central limit theorem tells us the characteristics of the distribution of sample means. We know ahead of time that the distribution of sample means will be centered on the population mean. We know that it will have a normal shape if the original population has a normal shape, or if the sample size is relatively large. We also know that the spread of the distribution of sample means, the typical amount of sampling error, the standard error of the mean, will be equal to the population standard deviation divided by the square root of n. That's a lot to know before you even start your study, and that will allow you to design your study more effectively. So the standard error of the mean is going to be summarized SEM throughout the chapter, throughout the whole book, is the typical distance between all possible sample means and the population mean. It's a measurement of expected sampling error. It follows this equation. And as I said, you can use the central limit theorem to compute the expected amount of sampling error, and you can use that to change your design to improve it. If you decide after doing computations that you want less sampling error, all you would need to do is either increase your sample size or reduce the variability in the dependent variable, perhaps by increasing the precision with which you measure it.